So our first talk is by Cauchemez, so that's the Institut Pasteur, and he's going to tell us about COVID-19 household transmission.
Thank you so much, Cecile. Can you hear me? So thanks first for the organizers. It's a great pleasure to be back. Last time was 10 years ago, and so very happy to be here again. So I thought I would talk about a concrete research project where we try to better understand the association between SARS-CoV-2 viral loads and transmission, looking at large household transmission studies in Nicaragua. And that's work done mostly by my PhD student, Thomas Cortier, working very closely with colleagues from the team of Aubrey Gordon at University of Michigan, and in particular Anna and Greg, who came to visit us last year in Paris to work on that project and other related projects. So what we are interested here is in better understanding the drivers of individual infectivity. We know that there are major heterogeneities in individual infectivities. It's quite common looking at infectious diseases that we hear that 20% of cases responsible for more than 80% of transmissions, and it appears to be like that for SARS-CoV-2. And if we look at the factors that are contributing to these heterogeneities, there's a long list on factors related to the intensity and the type of contact, to characteristics of the individual, like their age, also to the disease, whether or not you're symptomatic, your history of infection and vaccination, and also some more biological measurements, and viral load in the respiratory sample is one of them. And I think there's still quite a lot of debates on the relative contribution of these different factors, in particular the more biological ones, like viral loads, and the more behavioral ones. And so the aim of that work was really to try to look more closely at the viral load data we have and better understand the contribution of this specific biological measurement. And you can find in the literature quite a lot of studies that look at the association between viral load and infectivity being measured as whether or not you have viruses in your sample that can infect cells in a biological experiment. But it's quite far away from the kind of transmission probabilities we are interested in our models, where we really look at transmission between individuals. And if you look at papers on that association between transmission probabilities as we think about it and viral loads, there are not that many, and this is one of them done early on in the pandemic, where they looked at transmissions in high-risk contacts lasting more than 15 minutes. And so you can see here a very strong association between viral loads and this transmission probability, and actually little association when they looked at other types of contact. So quite interesting results, but also a lot of limitations in the study because it was small population, and they just have one metric for transmission, but they didn't account for all the heterogeneities you expect in the risk of infection, the possibility of multiple infectors in your households, different intensities and duration of contacts, risk of infection in the community, and also there was no control for other factors. And so we wanted to do the same type of explorations, but within the robust framework of household transmission studies, with all the associated models that we have for that kind of setting that can really control for heterogeneous risk of infection, and also having models that can both reconstruct the chains of transmission, which we usually do in that kind of studies, along with the viral load dynamics for each cases. So the type of questions we were interested in: how do viral load dynamics vary with individual characteristics? What's the association between viral load and individual infectiousness? And how much of the heterogeneity we see in transmission can be explained by viral loads? And that's the data we looked at. So Aubrey Gordon has been working in Nicaragua for years. So initially on influenza, and then during the pandemic, she extended her study to integrate COVID cases. So you have members of the community that are part of the study, and they go to a clinic, study clinic, and so when they are sick and are tested positive for COVID, then the household would be recruited. You would have both blood samples collected and also regular respiratory swabs, and also a follow-up of symptoms. And so from the respiratory swabs, we can quantify the viral loads. So we both need to reconstruct the dynamics of viral load in individuals and also to reconstruct chains of transmission in these households. So first, looking at how we model viral loads. First we say that, you know, when the person is infected, we initiate like viral loads with a very small level. Then we need to model the symptom onset with a distribution. So here we make an assumption actually from the data we have on the incubation period. All the analysis will be done for viruses like the pre-Omicron and the Omicron ones. And then we have this simple model for viral load dynamics where we are saying there's a proliferation time during which viral loads increase, then it reaches a max, and then there's a clearance time. So you really have three parameters that will estimate for each individual. And then what we are interested in is to see how these parameters will vary depending on the characteristics of the individual. So that's for the first part of the model. And the second part, there's already a long literature on how to model transmission within households. So you know, we have these follow-ups where we know who is infected first, and then we have symptom onset in the others. And so we describe chains of transmission within that setting. And so the model is quite standard. You have an hazard of infection for one individual J that will account for the specific characteristics of J, so capturing the increase or reduced susceptibility depending on the characteristics. Then the risk of infection can be due to infection from outside the household or transmission within the household. And then we are also accounting for the infectivity of the potential infector, again accounting for a list of variables that may impact their infectivity. And last, we model like the force of infection exerted from I on J. And usually the way we do that is by saying, you know, it's a function, this risk over time will be a function of time since the infection of I. So that's kind of this classical way to model that change in risk over time. And this is a function that like has been estimated a number of times in the literature. And what we're adding here is to saying, so there's still that part where we'll say it's not mediated by viral load, but then we are adding a term that will be dependent on the reconstructed level of viral loads for your specific individual, where you see you have a power coefficient here. And so we are summing a term that we consider as transmission not mediated by viral load, and then this new term that is capturing the effect of viral loads. For inference, I'll be brief, because there's has been like a lot of papers looking at that kind of methods. So we used Bayesian data augmentation methods to deal with the fact that some of the information we would need to be able to write down the likelihood are missing, like the dates of infection. And so we consider these dates as augmented data. And then we have a full Bayesian framework to do parameter estimation in that kind of context. The novelty here is that in addition to reconstructing, you know, the infection history, we also need to reconstruct the viral load dynamics. So this is showing like the data we have. So again, 2 period, pre-Omicron in green and Omicron. You see about 800 participants in each time period, slightly more secondary attack rates, so proportion of contacts getting infected during the pre-Omicron period than during the Omicron period. You can also see in the Omicron period, basically everybody had already been infected, you had high titers, and a lot of people had been vaccinated with the Sputnik vaccine. So if you look just at the raw data on viral loads, So you can see the kind of patterns that you expect with some rise and then decay. So as always in that kind of studies, you have quite a lot of individuals where you just have one measurement, but also a substantial number of them, about 40%, where you have at least two measurements. And what is very interesting for us is that just looking at the secondary attack rate within the household according to the viral load of the index case as it is measured, you see this doubling of the secondary attack rate from 22% to 40%. And this is, what we have here is not necessarily the peak viral load that we are going to reconstruct. So these are the viral load dynamics reconstructed for some cases, and again we estimate the proliferation time, the peak viral load, and the clearance time for each individual. And just maybe the one interesting result is we estimate, you see the proliferation time at 3 days compared to a bit more for the incubation period. So we are estimating that the peak viral load is just a bit occurring just a bit before symptoms. And so if we look at how these dynamics change with the characteristics of these cases, you can see that if you are asymptomatic or if you have high antibody titers to start with, you will have lower peak viral load and faster clearance. If you're a child, you have faster clearance, and if you have been previously infected, so just in the pre-Omicron period, you have a slightly lower peak. And so then we are moving to the part where we want to see how the risk of transmission is mediated by viral load. So currently, we're just looking at that first part, right? Where you see a very strong increase in that risk according to viral load with you see high power coefficient, where the way to interpret that number is that we're estimating that a twofold increase in viral load is associated with a tenfold increase in this viral load transmission risk. And again, this is just part of the transmission risk. We thought there was the part mediated by viral load and the one not mediated by viral load. So if we look at the other part, we find that all individuals, they have in the pre-Omicron period in household of size 4, about 19% probability of infecting someone else. And then this is increasing as a function of viral load. But so you see huge heterogeneities from 22% probability to 68, depending on whether the person had a high peak viral load. And you see that the effect is you still have an effect, but during the Omicron period, it's substantially reduced. And so overall, if we are just looking at the area under the curve, comparing the yellow part to the overall part, we find that during the pre-Omicron period, you have 59% of transmissions that appear to be mediated by viral load, and only 26% in the Omicron period. So this is how we think the risk of transmission is changing over time, where you have here both the part that is independent of viral load, and then that's the sum of the two. We were also interested in exploring a last question, which is so there are some features that we find to be associated with reduced infectivity, for example. And we wanted to see if that effect could just be due to differences in viral load in this individual. So to approach that question, we fitted a model, the classical model we use, where there's no viral loads. And here we estimate the impact of these factors, like being asymptomatic, on infectivity. And then we are doing the same process, but this time we account for the effect of viral load, and we want to see how this is going to change our estimates of infectivity. And so if we first look at what's happening for asymptomatic individuals, in this first model where we are not accounting for viral load, we find substantial reductions in infectivity for these individuals, but you see that once we start to account for viral loads, then the effect is no longer significant. And our interpretation of that is that the reduction we see in infectivity in asymptomatic individuals can be explained just by the fact that these people have lower viral loads. And so that's a first mechanism for asymptomatic people. And then if we look this time at whether or not these people have high antibody titers to start with, here you don't see much of a difference. So this is suggesting that for this second, here there's maybe another mechanism that is explaining these the changes in infectivity depending on antibody titers. And just looking at model adequacy, what's interesting is whether or not you account for viral loads in your models, you're always well able to capture like the overall size, final size, depending on how, so the final number of cases depending on the size of your household. But where it's getting interested is, I showed you earlier the differences in secondary attack rate depending on the viral load of the index cases. And here, clearly, you can see that a model that would not account for viral load dynamics wouldn't be able to capture these differences. And of course, a model that does account for that is doing much better. So I will stop here. Just showing a nice illustration of integration of within-host data and more general transmission data, where we found that viral load dynamics were affected by a number of factors, and that these viral loads were strongly associated with case infectivity, with an association that was actually substantially stronger during the pre-Omicron period, and that it appears the impact of some of our variables on infectivity, like asymptomatics, for example, may be mediated by viral load. And I think that's like a nice example of the need to think more about models that integrate like within host data with the more traditional transmission data we work with. And I will stop here and thanking again the different contributors of that work. Thank you.
Very nice. Any questions for Simon? Yeah, someone in the front here.
Thank you for a very nice presentation. So I was wondering about the infectiousness, or I don't know what the words, by the way, that your social activity does not drop so much within households when you become ill, whereas your mixing outside of the household might drop much more. I don't know, is that...
So I think actually during COVID, interactions within the household may have changed quite substantially. So so here we don't have the data on that. Like we have done simulation studies, because like in these household models, usually we make the assumption that everybody has the same risk of infection when you have a case in the household, and we know it's not the case. Like there's much higher risk of transmission from kids to their mom than kids to their fathers, for example, and so we need to collect better contact data in the household. And then in a session we had that was comments from Matt earlier this afternoon, there's also the question that when these people get sick, so during COVID, for example, in France, there would be a recommendation for them to be isolated in the household context, and that would be something else to account for in the model, which is difficult to do if you don't collect behavioral data. So should be a strong push to collect behavioral data within the household to also better understand how people change their behaviors when they are sick.
It's kind of a naive question, but nice talk, I want to say. But if you're not producing any viruses, you can't infect anyone. So I wanted to ask, what explains the part of the infection that's not connected to the virus?
I think the data we have on viral loads is not perfect. Like for a lot of the individuals, we have just one measurement, and then again, these viral loads, they are a proxy for like infectiousness. but the fact is that even people that appear to have very small viral loads, when we look at the data, so our initial model was just assuming that the risk was, linked to viral load, but then we were predicting much lower, secondary attack rates for a substantial group of individuals that we think had low viral load. So it's quite possible it's related to the reconstruction of viral load dynamics for these people, where maybe the model says there's no or very small peak, and actually we get it wrong on the peak. But that would be my explanation, that it's still quite noisy data. But the fact is that, the initial predictions we were making with that model, that you should have a group of individuals with 5% risk of infection, we don't see that when we look at the data.
Link to that. So first of all, can we just assume that actually that gamma shape worked pretty well because it is a proxy for viral load? And I could imagine that just changing that shape a bit, something which works really well. But then linked to that, the people you have more than one reading, how predictable are people's viral load? How often do we take into these viral loads? It's actually quite a predictable shape. You take one, you can actually recover, generally speaking, that trajectory.
So first on these shapes, so initially we want, I'm not sure what it is. We wanted it may be a bit circular in that the part of the risk that is not associated with a viral load, we are saying, well, it's around the same times, and maybe it's kind of like self-feeding. We try to estimate that other part, and then we just don't have the power. And so this is the part taken from the literature and all that, but I think we reached the limits of what we can do with this data. And then for the, where are the data? I'm not sure. But then for the dynamics, the viral load dynamics, so they are usually pretty well explained with that simple model. And when you look at the literature on within-host models, you can get much complex models, but they end up with something that often looks a bit like, these triangles. And I think where, it may be where we may potentially get it a bit wrong is on the fact that for a lot of people, we just have one measurement of viral load, so then obviously it's the limit. But what's interesting is that, again, just looking at the raw data about the peak variable, if we use our models to fit that without the transmission model, and then we use the peak viral load here, so we haven't looked at the transmission data, but then we are trying to predict secondary attack rates. From that data, we get a very good estimates. And that's, for me, is like very reassuring that it's not just something circular.
We have to move on, but we'll take just one quick question on Slack. So you added the viral load term with the non-viral load term. Right? How about not adding them?
So we tried, my PhD student, we tried a lot of things. Okay. We're happy to try. I'm not sure we tried that. But I think, if you're multiplying, it's just the viral load model, because it's already like a beta times viral load. We tried. There are a lot of. It's not so easy to reproduce some of the patterns, and the key was coming back to the point that was made earlier, that for a long time we were not able to explain that you always have quite a lot of transmission, even in people that don't have a high estimated viral loads.
Very good.
Thank you.